So welcome to this is the Further Math Support Program online revision session for Edexcel S3. And what we're looking at in this session is the two major applications of chi-squared testing. So those two applications are the ability to perform a hypothesis test for association of categorical data, which is going to be the first question I'm going to look at, but also, slightly more interestingly, is to be able to perform a hypothesis test for a goodness of fit. And you need to be able to do this for many things. So your original distribution may be binomial, Poisson, or normal, or even uniform, which are standard things that you may be asked, but also it could be a bit more adventurous, and you may be told that your underlying distribution fits a particular ratio, say, I don't know, 1 to 2 to 2 to 4, and you've got 4 categories across one side. Or it could be continuous, so like on S2 you may be given some sort of function to work out your probabilities. So as long as you can work out the underlying probabilities, you can then multiply up by your sample size to get your expected values in that context anyway. So just be very aware that you may be given a distribution that is unfamiliar to you, but that really shouldn't matter. Okay, so June 2010, question 5. We've got a random sample of 100 people, and they were asked if their finances were worse, the same, or better than they were last year. The sample split according to their annual income, and results are shown. Okay, so we've got three situations: worse, same, better, and what their annual incomes were. And we're to test at 5% level of significance whether or not the relative state of their finances is independent. Now, I much prefer to use the word not associated, or associated in that context. Okay, depending on what you're asked to do. And we're asked to state hypotheses and show working clearly. So here we go. So firstly, what we need to be aware of is how to work these out. So we could really do with some totals. Okay, that's going to be a total of 34 and 66 with a grand total of 100. Now we need some hypotheses. Now I like to involve the word not in my null hypothesis. So what I'd be stating here is that the state of finances and income are not associated. I just prefer that terminology. You could use independent if you wished, but I just prefer the word not associated. And then H1, again, don't paraphrase, write it as it is. So state of finances and income are associated. Okay, so to do this, what we have is a table of what we call observed data. So we've got 011, 012, 013 and so on, and 021. And what we're looking for is expected values such that the distributions are independent in both directions. So there's a way of doing this. And basically, to work out each expected value, we're going to take each row total for each cell, divide it by the column total, and divide by the grand total. So for instance, this implies that E11 is going to be row 1 times by column 1 total over grand total, and that's going to give me a value of 10.54. Now this is the interesting thing. Once I know that this is 10.54, I can actually work out the other value without needing to use expected value formulae, because it must add up to 31. So I know for a fact, just change my ink color, sorry. I know for a fact that this value here has got to be 20.46. Okay, now same argument, we can do the same thing for the next cell. So if I work this one out, so E row 1 column 2, that's going to be 34 again times 31 over 100. Now I'd expect that to be the same because it's the same grand total. So that's going to be 10.54. And again, once I've worked that one out, I can be very aware that these follow. So that's going to be 20.46, and I can actually now work out the others as well. So this is going to be 12.92 and 25.08, and that's because they add up. So notice I've only actually had to fill in 2 cells to generate the whole table, and this is going to give me some ideas about what these degrees of freedom are. Okay, so in this particular case we have 2 degrees of freedom, but of course there's a way of working it out, which is row minus 1, column minus 1. And that's how we would do that. So I'll use that application a little bit later on. Okay, so if I do that for each of them, we've got 6 values, and that's what they're going to be. Oops, sorry, 25.08. Let's change that now. Okay, so what I need to do is one of two things. For each pairing, so there are 6 in total, I can either work out O minus E squared over E, or I can work out O squared over E. Now some of you may not have seen this, but it is a little bit quicker. So let's just look at the first pairing. Okay, so to work this out, we're going to have O minus E, so this is going to be 14 minus 10.54 squared over 10.54. And if we work that out, that's going to give me a value of 1.1358 and lots of stuff. This one is going to give me something slightly different, and that's nothing to worry about, and I'll show you how it works in a minute. So this is going to be 14 squared over 10.54, which would lead me to a value of 18.59, etc. And again, don't round these too much. Always do at least 5 significant figures, so that you're not going to have any rounding errors as and when we need. So what we're going to do is we're going to do this for each of the 6 pairings. Okay, so there we go. Now, I haven't really talked about how the marks are allocated yet, so let's just go back and just think about that. Okay, so in this particular case, we need to be working out our expected values. And by working out your expected values, you get M1A1, depending on how many are correct. You get an independent B mark for writing out your hypotheses, and then from here, working out your either this column or this column, we're going to get 3 marks. So we're going to get M1A1 for correctly working out either of these 2 columns, but then it's working out the test statistic. So there are 2 ways of doing this, depending on which process you've used. So your test statistic is either the sum of all of your O minus E squared over E values, or it's the sum of your O squared on E values minus 100, which is your grand total. Okay, both of those will give you exactly the same answer. Okay, so if you do this one, this will give you 3.553. This one will give you 103.553 minus 100, which is again going to give you 3.553. So you're going to get your final accuracy mark here for getting that correct value. Now, whenever you're doing a hypothesis test, you've got your test statistic, you need to work out your critical value. Now, for the chi-squared, we are dealing with these things called degrees of freedom. We've already established that there are 2 just by how we think about filling the table in. But again, we've got this row minus 1, column minus 1 idea. So that's going to give me 2 minus 1, 3 minus 1, which is going to give me 2 degrees of freedom. Now, please write this, okay? Just in case you get it wrong, at least we can see method marking for where it's going to be. So you get a B mark for this, which is quite nice. So we're looking at your test statistic is going to be the chi-squared statistic with 2 degrees of freedom at the 5% level. So we're dealing with a 5% level with 2 degrees of freedom. So your critical value is going to be 5.991, and that triggers you your next B mark. Okay, so your final 2 marks for this question for actually carrying out the test fully. So your test statistic was 3.553, and I can see that that is less than your critical value. That basically means you're not in the critical region. So therefore, we do not reject H0. Okay, so that gives you a method mark, and then we fully contextualize. So there is insufficient evidence to suggest that. And then what you need to do is go back to your hypotheses and literally quote it. So I said to suggest that state of finances and income are not associated. Okay, and it's the safest way of doing it. There are other ways of doing it, but always go back to your full question. Okay, and that's where your final accuracy mark is coming. So that's a typical sort of good contingency table approach to this. Okay, right. So the other thing you need to be able to do is you need to be able to fit a distribution or show that it fits. And again, please don't be shorthanded in the way you write things for this. So here, number of hurricanes per year in a particular region was recorded over 80 years, and the results are summarized. Write down 2 assumptions that will support modeling a Poisson. So again, a nice little bit of S2 just to remind you what's going on. So we've got a variety of things. Hurricanes occur singly. So hurricanes occur singly. Now some people say they may not, but these are about your assumptions, don't forget. Okay, they occur at random. And again, these are assumptions, not what really happens. And the fact that they're rare is actually quite interesting. Okay, and they act at a constant rate. So any of those would be absolutely fine. Okay, so the ones that you're more likely to write is occur singly, occur at random, and occur at a constant rate. Any of those will be sufficient, I think. So you get 2 marks, one for each that you're going to write. Okay, so show that the mean number of hurricanes per year is 4.4875. So they've quoted that because you're then going to need to use that later in the question. Okay, so we've just got to show that it's going to be true. So this is a nice frequency table. We're going to do 0 times 0, plus 1 times 2, plus 2 times 5, etc., all the way up to 7 times 12. You need to make sure you're writing all of these, what I've written out. You need to give me some indication that you've completed the mean. Okay, so that will be absolutely fine. Nothing is incorrect with that. So we can then, get your 2 marks for doing such. So you get 1 mark for demonstrating method, and accuracy mark for actually getting 4.4875. Okay, so please make sure you're writing sufficient there. Okay, so we're then asked to use the answer in part B. So that was the fact that your Poisson variable is 4.4875 to work out expected frequencies for these. So your expected frequency for 2, for instance, is going to be 80 multiplied by the probability that your value is going to be 2. And of course this is Poisson. So it's going to be 80 multiplied by. So lots of ways of doing this. Okay, but the most simple way of doing it is to just work it out. So it's going to be e to the minus 4.4875 times by 4.4875 to the power of 2 all over 2 factorial. Okay, and if we work that all out, that's going to give me 3 significant figures, 9.06. Okay, now when you work out S, it is absolutely critical that when you work out S, you do it in such a way that your total expected frequency is 80. Okay, if you don't do that, you can lose a lot of marks. Okay, so S is going to be all of them taken away from 80. And if you do that, you're going to get an answer of 15.205 effectively. Okay, you could do these the other way around, but we really are looking to make sure that your expected frequencies add up to 80. Okay, really quite critical. So that's that done. So you get 3 marks basically for working out those. Okay, so you get a method 1 mark for using the formula correctly, and then 2 accuracy marks for each. Okay, so carries on, and it then, so there we go, there we go. And then it asks us to do a hypothesis test. Now, one of the critical things you need to be very, very aware of is you need to make sure that your expected values, when you're doing a goodness of fit test, exceed 5. So we have a bit of a problem down here. Okay, so what we have to do is we have to combine these 3 groups together. Okay, so that we get an expected value that's greater than 5. We really are meaning greater than 5. Okay, some people argue that it's close enough, so we can get away with it, but the mark schemes are designed in such a way that we're dealing with greater than 5. So that's where the 13.9991 comes from. So the key thing to recognize here is we actually have 6 categories combined. Okay, and that's going to be very, very important when we come to degrees of freedom. Okay, so that's how we combine them. And then what we need to be able to do, again, in each case, is we need to be able to work out the difference between observed and expected data. And we, again, can do this in one of 2 ways. You can either work out O minus E squared over E, or you can work out O squared over E. Both are perfectly acceptable. Okay, and again, if you sum your O minus E squareds over E, that will give you a value of 6.545. If you work out your sum of O squared on E, that will give you 86.545. So for your test statistic, you need to remember it's O squared on E minus your grand total. So your test statistic, irrespective of which method you're doing, is going to be 6.545. Now notice I haven't actually written a hypothesis yet. It might be a good idea to do that in a minute. So yeah, we'll do it now actually. So H0 is the fact that the Poisson is a good fit. Now all I'm asked to do is, can it be modelled by a Poisson? I'm not told what the parameter is. I'm just asked. So don't put a parameter in. An H1 will be Poisson is not a good fit. Okay, so that's my hypothesis. Please don't use symbols. Please don't use shorthand. Please don't write X is Poisson. Don't do things like this. That would be whatever it was. That would be completely incorrect. So don't write those. Use words again, please. Okay, so again we need to think about degrees of freedom. So the general rule of thumb is degrees of freedom is n minus 1 minus the number of estimated parameters. Again, I suggest you write this. So n minus 1. N is the number of combined cells. So we have 6 minus 1 because there were 6 combined categories, and we had to estimate lambda. So we need to subtract another one. And I'd much prefer to see 6 minus 1 minus 1 than 6 minus 2. So we're dealing with 4 degrees of freedom here. Again, we're looking at the 5 percentile. So we're looking at chi-squared with 4 degrees of freedom at the 0.05 level, which is going to give me a critical value of 9.488. So again, I can see that my test statistic is less than that. So I can see that 6.545 is less than 9488. So again, this puts me not in the critical region. So do not reject H0. Okay, so this is implying that we can, I don't like saying accept, but we kind of do. So therefore, there is sufficient evidence to suggest that hurricanes can be modelled with a Poisson or by a Poisson. And again, no reference to the actual parameter because I don't know what it is. I had to estimate it. Okay. So again, they're the 2 key ideas about what we need to be able to do with chi-squared. And again, make sure you're fully aware about goodness of fit and you are able to do it with distributions where it's not a known distribution. But again, as you can see, as long as you can work out probabilities, then these are generally pretty okay.